Hello and welcome. My name is Noah Deere, and this is the Math 254 at Portland Community College Vector Calculus sequence. This lecture is Lesson 1, Vector Valued Functions. We are going to give some introduction to vector valued functions, some definitions, how they relate to parametric equations. Then we're going to go ahead and get into graphing vector valued functions, how we can do that if these vector valued functions are in 2 dimensions or 3 dimensions, and how we can use tables or technology in order to see what these functions look like. And then we are going to look at when you have 2 vector valued functions, whether or not they actually intersect with each other, and if they do intersect with each other, determine what angle they intersect with each other. And if they collide, if they could potentially intersect at the same time, or if they cross the same point in space but at different times. So let's go ahead and jump right in. All right. Introduction to vector valued functions. From previous classes, the topics of vectors, planes, and functions have been covered. We may now think of these ideas together by defining a function in 3D space in terms of some parameter t, for example. This is merely a natural progression from parameterization of functions in 2D space. So we're going to look at an example here in just a second. Let's do a formal definition real quick. Definition 1.1.1. A vector valued function is a function with a single variable input and a vector output. That is, it is a function that outputs a vector whose components are determined by the same input variable. So note, vector valued functions are more simply just parametric equations but written in vector notation. We're going to take a look at all of this in this example right here. So example 1.1.1, let r of t, note this bold right here, indicates that this is a vector. We want to keep in mind that if we're doing this by hand, you want to write r of t like this, equals, and then we'll have our x, our y, and our z values in these angle brackets, or we can use the ijk notation, I want to use x again. So this is my x value plus my y value times the j direction plus the z value times the k direction. Okay, so let r of t equal the vector f of t, comma g of t, comma h of t. This is my x, or I want to say change in x. This is my change in y. This is my change in z. And that's because this is a vector, so we're saying that this is the change in x in the x direction, right? Because a vector gives us our direction that we're going from any point. So we're saying we're moving this much over in the x direction, we're moving this much over in the y direction, we're moving this much over in the z direction. It's not saying from some specific point. And so we're saying that f, g, and h are all real valued functions. So f of t takes a real valued number, t, and outputs a real valued number, x. The function r of t is called a vector function. Let's get an idea of what this is doing here. So here I'm going to have my axes, my x, my z, my y. Oh, that's not the straightest line. My y-axes here. So we're in 3-dimensional space, and I could take and plug in, say, 0 for t, and we're going to call this r sub 0 for a specific vector here, and this gives me x naught, which equals f of 0, y naught, which equals g of 0, and z naught, which equals h of 0. And we correspond this now to the point p naught, which just equals the point x naught, y naught, z naught. So this is outputting a vector, and we're going to even though this vector could be anywhere in space, we're going to start it from the origin and say that this vector is here. So r naught points to this point p naught. So even though vectors can be anywhere in space, the way that we think about these vector valued functions is that the vectors that we're outputting are pointing to the points that correspond exactly with what the change in x, change in y, and change in z are from the vector function. So the vector outputs are technically changes in x, changes in y, and changes in z, but for the vector valued function purposes, we think of these as outputting the point x naught, y naught, z naught. So we could do this again for some other time, say when t is 1. And we'll call this r sub 1. And this is going to output the vector f of 1, g of 1, h of 1. And say this vector is here. And we will really think of this as corresponding to the point p sub 1, which equals x sub 1, y sub 1, z sub 1. And we could keep doing this for different t values. And if we did that for all of the t values in the real numbers, then we could end up with some curve like so. And we're going to draw arrows on here to indicate the direction so that as t is getting bigger, that the curve is moving in this direction. So that we can actually bring this into thinking about motion in space. If I have an object that's traveling through space, we can say, where is it at different points in time? What is its path of motion? In what direction is it traveling? And we had above here the note that vector valued functions are more simply just parametric equations but written in vector notation. So the vector equation would just be x of f of t, y equals g of t, and z equals h of t, and we think of these as outputting points equal to x, y, z. But the reason that we do this with vectors instead of points is that we have an algebra for vectors. We have our linear algebra that allows us to add vectors, subtract vectors. We'll eventually get into dot products and cross products of vectors and work with these space curves in ways that are developed through algebra and calculus. We'll be able to take their derivatives and their antiderivatives and use those for finding solutions to applications as well. So a couple of quick notes here. The function defines a curve in 3D space. This type of function arises in many physical applications, for example in fluid mechanics. The arrow on the curve represents the direction for which the curve is generated as t increases. So let's get into doing some examples and talking about what some of these look like. Here, example 1.1.2, determine the domain of the vector valued function r of t equals the vector. The x component is the square root of 4 minus t squared, comma, the y component is e to the negative 3t, comma, the z component is the natural log of t plus 1, all inside the natural log. So the definition of a domain, it's the set of all. The domain equals the set of all t values which are in the real numbers such that these t values will actually work in this equation. So what we need for our domain is we need whatever t value we plug in to actually work in all three components, not just one of them. So we need, for the first component, we have 4 minus t squared has to be greater than or equal to 0. The second component's not going to have any requirement for our t because we can plug in any t into this exponent, multiply it by negative 3, and take e to any number. So no restrictions due to the y component here. For the z component, the natural log has to have inputs that are greater than 0. The inputs are given by t plus 1, so t plus 1 has to be greater than 0. For our domain, we need all of these to be true, so I'm going to put the word and right here. We need this to be true, and we need this to be true. And we're going to solve each of these. So here I can say negative t squared is greater than or equal to negative 4. T squared is now less than or equal to 4. And we flip the inequality here because I divided by negative 1. And this actually shows that negative 2 is less than or equal to t is less than or equal to 2. So think about this for a second. Make sure that you're seeing that these two inequalities are equivalent statements here, right? So the square root of 4 is negative 2 and 2, if we're allowing for the plus or minus. And we want our t values to be such that we're getting, when we square them, we get less than or equal to 4. So any t value between negative 2 and positive 2 will work. Over here, we just bring the 1 over to the other side. T is greater than negative 1. We need both of these. So if I combine these two ideas to look at a single interval, tongue-tied here, t has to be greater than negative 1 and has to be less than or equal to 2. So both of these come into play. And we see that the numbers between negative 2 and negative 1 are actually not going to be part of our domain, even though that they're allowed in this component for x, they are not allowed in the y component. Numbers bigger than 2 are not allowed for the x component, even though they would be fine in the z component. So we bring these together and it becomes this single interval. So I'll just write that in here. And there's my domain. We can write this in interval notation from negative 1 to positive 2. Either of these are fine. You should really be comfortable writing this out in either notation, reading it in either notation. So go ahead and look at exercise 1.1.1. And you're going to pause this video. This is really important, that you realize that math is not just about watching me do it, but about you doing it. So I want to give you an opportunity right here, right away, before spending the next hour watching this video, to get your hands dirty in the moment. So pause the video. Hopefully you've printed out the lecture notes. If you haven't yet, go ahead and take a moment. There should be a link above here that allows you to print out the blank lecture notes so you can go through and work this with me. So pause the video, you try this on your own, determine the domain of the vector valued function r of t equals the vector square root of t minus 5, comma 3t squared plus 5, comma 1 over t, and I will go ahead and work out the solution and talk you through it in a few moments. Alright, so it's only been a few moments in video time, but hopefully you've paused and worked through this. If I look at my vector valued function, r of t equals the vector square root of t minus 5, comma 3t squared plus 5, comma 1 over t. I look at the x component. I recognize that t minus 5 has to be greater than or equal to 0. The second component is not going to give us any restrictions on my t value, but the third component is going to give me that t cannot equal 0, since we can't have zeros in denominators, so I write that out as well. T cannot equal 0. And then I'm going to go ahead and simplify this one on the left, t minus 5 greater than or equal to 0. Just move that 5 over, t is greater than or equal to 5. And the other one, t cannot equal 0, is not going to change at all. If I bring these together, I recognize that this is just saying that t has to be greater than or equal to 5, because 0 is already less than 5, and I don't need to repeat that statement. So we're going to write our domain equals the set of t such that t is greater than or equal to 5, close set brackets, which in interval notation equals the set hard bracket, the interval hard bracket open 5, comma infinity soft bracket close. Alright, the next thing we want to look at is we want to look at limits of these vector valued functions. So if I have we essentially want to say, okay, if I have this space curve and it's doing something and this is not for this vector valued function, this is just a quick idea of what's happening. So my limit is as t goes to infinity, so I could have some space curve that's doing all sorts of things, and it may just be coming down and it may be slowing down to some single point. Or it could have some sort of linear asymptote. So I could have something else where it's approaching some linear behavior, or maybe it's just shooting off into infinity. And so we just want to be able to have a way of determining where this function is going as t goes to infinity. So if we were talking about an object in space, what's the trajectory of this object? Where is it going to end up if we just let it keep moving on its given programmed course here? So as I do this, we can really just take the limit of each of these components individually and see what's going to happen to them. And I'm realizing I'm writing way too big for this problem, so I'm going to squeeze this down a bit. Okay, so in order to take this limit, I'm going to look at the limit of each of the components individually. So I'm going to look at the limit as t goes to infinity of 2 plus t squared, the limit as t goes to infinity of the natural log of 1 over t, and the limit as t goes to infinity of one of my favorite limit examples is e to the arctangent of t. Barely squeeze that in there. Okay, so the limit as t goes to infinity of 2 plus t squared, there's nothing weird going on with this. This just goes to infinity, right? The 2's not doing anything. It's t squared. As t goes to infinity, t squared goes to infinity plus 2. We're going to infinity here. No big deal. The next one's a little bit more complicated. The limit as t goes to infinity of the natural log of 1 over t. So hopefully you guys have worked with enough of these that they start to become a little bit intuitive. What's happening here is 1 over t is going to this is going to go to 0, right? As t goes to infinity, this is going to go to 0. I'm going to introduce a new variable, a. Whoops. And we want to pay a little bit more attention here. So I'm letting a equal the inside function. The inside function doesn't just go to 0, it goes to 0 from the right side. It's going to be a positive 0, right? We're not going to be hitting negative values if t is going to positive infinity. So positive 1 over positive infinity is going to positive 0. So my a, which equals 1 over t, this inside of this natural log, is approaching 0 from the right. Now to take this, this is being familiar with the natural log function in some good detail. So the natural log function, I'm going to get another color here, has a vertical asymptote here, and this is its shape. So as the natural log, here we have a as our input, the natural log of a is this red line, and as a goes to 0 from the right, we see that this is approaching negative infinity. This is going down to negative infinity here. So that's going to be my second limit for the second component. Finally, we need to look at the limit as t goes to infinity of e to the arctangent of t. And the key here is to know that the arctangent looks like this, where it has horizontal asymptotes at negative pi over 2 and at positive pi over 2. So as its input goes to infinity, its outputs are going to pi over 2. So this equals e to the pi over 2. And that's it. There's nothing else going on here. E to the pi over 2, that we could get a decimal approximation, but we don't want to. We want to leave it in a nice exact value here. So our answer then is infinity, negative infinity, and e to the pi over 2. And that's it. So you guys go ahead and take a moment to do the following exercise, 1.1.2. Find the limit as t goes to infinity of the vector 1 plus t squared all over the quantity 1 minus t squared. Second component is the tangent inverse of t, and the third component is 1 minus e to the negative 2t all over t. Go ahead and give that a try. And I will come back and work through the solution with you in just a few moments. All right, and we're back. So to find the limit as t goes to infinity of this vector valued function, I look at each of the components individually. So the first component, I take the limit as t goes to infinity of 1 plus t squared all over the quantity 1 minus t squared. Here, as I take this limit, since t is going to infinity, the ones on the top and bottom are not really helping us, or they're not doing anything for the overall ratio. As t goes to infinity, these constant values are doing essentially nothing. So we just drop them. So this equals the limit as t goes to infinity of t squared over negative t squared. The t squareds cancel, and we get that this limit equals negative 1. For my second component, I have the limit as t goes to infinity of the arctangent of t. And as we saw in the previous example, scroll back up here, we have that this is the arctangent function. Which is the same thing as the tangent inverse of t. Oops. And we saw that the limit as t goes to infinity of this function is pi over 2. And for our third component, we have the limit as t goes to infinity of 1 minus e to the negative 2t all over t. I'm going to rewrite that as the limit as t goes to infinity of 1 minus the fraction 1 over e to the negative, 1 over e to the positive 2t now. So I've just switched the negative exponent into a denominator. And this is all over t. This limit equals 0. Let's take a look. If I'm looking at top, the first term is 1. The second term is going to go to 0. The bottom is going to positive infinity. So this is 1 minus 0 over infinity. So that's just 1 over infinity is 0. Here I have scratch. This is not formal notation. We are not allowed to put an infinity in a fraction formally, but in scratch work it's kind of nice to just kind of see that. So that's essentially the arithmetic that is happening here. All right, so I have the limits of all three components. I plug them in. So the limit as t goes to infinity of the vector function 1 plus t squared all over 1 minus t squared, comma, t to the negative 1 of t, comma, 1 minus e to the negative 2t all over t equals the vector negative 1, comma, pi over 2, comma, 0. And that's everything we're doing for this example. So hopefully you guys have that worked out. Let's move on to the next page. Next section, 1.2, graphing vector valued function. So we're going to start by doing this in 2 dimensions first, and then expand this up into our 3-dimensional cases on the next page. The first example we're looking at, example 1.2.1, sketch the curve given by the vector function r of t equals the vector t cubed, comma, t minus 1. So we're going to do this in some detail by setting up a table first. So I have a table, write out a table. The first column is going to be t values. My second column is going to be my x values that we're going to get from the first component. This, in our case, is t cubed. And the third column is going to be our y values, y equals t minus 1 in this case. So we'll start with, say, negative 2, negative 1, 0, 1, and 2. Note that I could change these t values up. I'm using negative 2 to positive 2 as a starting place. I may decide that I want to change them. I'm also thinking whole numbers because I have cubic functions and linear functions that are all, there's no big numbers in these at all. So I just want to stay nice and close to 0 for my t values and not do anything too crazy. But remember, we could plug in any t value we want to find the point that it corresponds with. So if t is negative 2, my x value is going to be negative 8 after cubing. My y value is going to be negative 3 when I go negative 2 minus 1. I'm just going to do that for all of these. So negative 1 cubed is negative 1, 0 cubed is 0, 1 cubed is 1, 2 cubed is 8. When I plug these into my y-coordinate, negative 1 minus 1, negative 2, 0 minus 1 is negative 1, 1 minus 1 is 0, 2 minus 1 is 1. And these are going to give me my points, which are technically vectors, but we think of them as points on my coordinate plane here. So this is a plane curve as opposed to a three-dimensional space curve, but the concept and how we're graphing these is exactly the same. So when t is negative 2, we have the point negative 8, negative 3. So if I want to be able to get that on here, I'm going to say that these are going by 2's. In my x direction, my y direction I'll just have be going by 1's, it looks like, since we're not getting any really big y values here. So it's going to be, we're essentially stretching this or compressing it in the x direction so that all of these points fit. So negative 8, negative 3 is this point here. Negative 1, negative 2 is this point here, which means I'm going to go ahead and erase this, put it on the other side. And then we have 0, negative 1. Whoops. Is here. Then I have 1, 0. I don't normally have this problem. And then 8, 1 is here. Now, even though, so let's write it like this. This is t equals negative 2, which corresponds to the point negative 8, negative 3. And if I connect all of these points, then we get this curve here, and we note that it's going in this direction. I'm not going to label all of these points in this case, just enough to get the idea here. So we see as time is moving forward, we're going in this direction. Let's keep in mind that technically the vector valued function is outputting, this is r of negative 2 is this vector here, but we don't actually draw this vector in. This is technically r of 0, but we're not going to draw this vector in. What we're really interested in is the blue line, our space curve that is created as time moves forward. Again, we think of these as really the parametric equations x equals t cubed, y equals t minus 1, as opposed to a vector function, even though it is technically a vector function so that we can use algebra and calculus on it. We really just think of it as the points that correspond. Okay, and that is everything we need for this example. Go ahead and move down here. This exercise is for you guys. Go ahead and take a few moments, pause the video, try and work this one out on your own, and I will go through the solution here in just a few moments. All right, let's run through this. Again, we're sketching the curve given by the vector function r of t equals the vector cosine of t comma t squared. So I want to set up a table of t values that are going to work for these x and y values. The frustrating thing, or the thing that we need to come up with a solution for, is that the x values are given by a cosine function and the y values are given by a t squared function. So we have to decide, do we want t values that are whole numbers, or do we want t values that are somehow working with fractions of pi? And I think the best solution here is to deal with t values that are fractions of pi. I've plugged in t as 0, plus or minus pi over 2, plus or minus pi, plus or minus 3 pi over 2, and plus or minus 2 pi. I really want to work with exact values. If you look at my solution, I have not used a calculator in any way, shape, or how for this entire problem. So my x is given by cosine of t, so I fill in this column here for my t values. If t is 0, x is 1. That is, cosine of 0 is 1. If t is plus or minus pi over 2, the cosine of plus or minus pi over 2 is 0. And I'm getting that from just my unit circle values for the cosine, which you very much need to be familiar with. If you are rusty in any way on your unit circle, you need to look that up, Google it if you would like to, and just refresh that. That is not something we're going to go through in this class in any way, so look that up if you need to. But my cosine values are my x values on my unit circle. This is 0, 1. This is negative 1, 0. This is 1, 0. And this point at the bottom of the unit circle is 0, negative 1. So I'm just pulling off of this. If t is plus or minus pi, the cosine of plus or minus pi is going to be negative 1. If t is plus or minus 3 pi over 2, then cosine of plus or minus 3 pi over 2 is 0, and the cosine of plus or minus 2 pi is 1. If I take these t values and plug them into my y column, y equals t squared, then if t is 0, 0 squared is 0. If t is plus or minus pi over 2, then plus or minus pi over 2 squared is 1/4 pi squared. I'm just leaving that exact. If t is plus or minus pi, then I square that and I get pi squared. If t is plus or minus 3 pi over 2, then I square that and get 9/4 pi squared. And if t is plus or minus 2 pi, then I square that and get 4 pi squared. So my points that we're going to go ahead and write down, use this in blue, are the points 1, 0, 0, 1/4 pi squared, negative 1, pi squared, 0, 9/4 pi squared, and 1, 4 pi squared. So since every y value is a multiple of pi squared, I'm going to go ahead and say that each of my tick marks on the y-axis are worth pi squared. So I haven't labeled the first one, but we see the second tick mark is 2 pi squared, the fourth one is 4 pi squared. So pi squared would be, like 0, pi squared would be right here at this point. So if I want to, and in my x direction, I've actually stretched this a little bit, so every tick mark is worth 1/2, so 2 tick marks is where my x equals 1, and negative 1 is back here at the second tick mark to the left of the y-axis. So the point 1, 0 is right here. The point 0, 1/4 pi squared, well, that's, if pi squared is right here, 1 unit above the x-axis, then 1/4 pi squared is just 1/4 of that distance is right here. So this is t equals plus or minus pi over 2, and that gives us the point 0, 1/4 pi squared. Similarly, if t equals plus or minus pi, we get the point negative 1, pi squared. Pi squared is at this first unit above the x-axis, so negative 1 is to 2 units to the left of the y-axis. We get this point here, and so on and so forth, plotting all of these points. We then see that as t goes from 0 to infinity, I've got these orange arrows that are showing that we're moving away from the point 1, 0 along this stretched out sinusoidal path here in the y direction. And note also, if t goes to negative infinity, we also are moving away from that. So if we start at 0 and either go to positive infinity or negative infinity, we are moving up along this stretched sinusoidal path, as indicated by these orange arrows. As t goes to plus or minus infinity, we get in this direction. On the other hand, if we're approaching 0, actually I could say that this is from either direction. I'm going to go ahead and actually just erase this and say that this is from plus or minus infinity. So if we're coming from large numbers, whether they be negative or positive, and come towards 0, then we're coming along the green arrow direction back to the point 1, 0. All right, and that is all we need to do for this problem. Okay, moving on to the next page, we're going to do this same process, but in 3 dimensions. The first one's not going to be too much more difficult. let's read it. I'll explain what I mean. Example 1.2.2, sketch the curve given by the vector function r of t equals the vector 1 comma cosine of t comma 2 sine of t. What we see here is that my x value is just always 1. So we're really going to be looking essentially at a plane curve where the y value is cosine of t, the z value is 2 sine of t, and x is not going to change at all. So this makes this kind of simple in comparison to where these can go. Here we already have a table drawn out for us, so we're going to be plugging in some t values. Since we're dealing with cosines and sines, the t values I want to choose are going to be 0, pi over 2, pi, 3 pi over 2, and 2 pi. We could adjust these if necessary, if we needed more detail to this, but these should hopefully do us well for this problem. Note that my x value is 1 all the time, so I can just fill that in real quick. My y values are given by the cosine function, cosine of t. So cosine of 0 is 1, cosine of pi over 2 is 0, cosine of pi is negative 1, cosine of 3 pi over 2 is 0, cosine of 2 pi is 1. Go ahead and pause and run through that again if you need to. Note that y is being defined to be the cosine function of t for this problem. This is not the same as our unit circle. This is defining a new function, y of t equaling to cosine of t. We'll look at the graph on Geogebra here in a second, kind of relate how this is all coming together as well. For our z values, we have z equals 2 sine of t. So sine of 0 is 0. Sine of pi over 2 is 1 times 2 is 2. Sine of pi is 0. Sine of 3 pi over 2 is negative 1 times 2 is negative 2. Sine of 2 pi is 0 again. So now that I've got these written out, I'm going to go ahead and get my axes set up. And what I'm going to do here is I'm actually going to call this so normally we would have the x-axis moving off to the right, the positive y-axis moving out beyond to the back. But because my x value is constant at 1, I'm going to have my x-axis coming out the front and my y-axis moving out to the right. And that's essentially, I've just rotated. So previously we would have had the positive y-axis here, the x-axis here. If I rotate that 90 degrees, I'm just bringing my x-axis to the front and my y-axis out to the right. So my x-axis, just have a negative 1 and a positive 1 here. My y-axis looks like we're going 1, 0, negative 1, 0, 1. So we just need that to be, just need negative 1 to 1 on my y-axis. My z-axis, we have 0, 2, 0, negative 2, and 0. So let's get negative 1, negative 2 on here. And then we'll get our points plotted. So I'm going to switch colors for this. First point, 1, 1, 0. So all my x values are at 1, so I'm really going to be coming off of here. For everything I do in this problem. I'm just going to draw some dotted lines to help me keep everything in this plane of x equals 1 here. So the point x is 1, I'm not going to worry about that. I'm just going to stay in this plane. Y is 1, z is 0. Let me do one more color. Okay, so y is 1 is this length. So I move over that length here. Z is 0. I'm just going to be at this point right here. When t is pi over 2, my y is now 0, and my z is 2. So 0 in the y direction, but I'm going to go off of these axes. So 0 to the right and 2 up. It's going to be about 1. 2 is right about here. It does that whenever I'm trying to draw in a single location for too long. It's like if you hold it down, it does this to open the menu. So it thinks I'm just holding it down for that. So at that point, there, let's label these. So this is when t equals 0, which is the point 1, 1, 0. This is the point when t equals pi over 2, which is the point 1, 0, 2. And then if t is pi, we get x is still 1, y is negative 1, z is 0, so I go negative 1 in the y direction. This distance is about here. So this is t equals pi is the point 1, negative 1, 0. And then we have the, when t is 3 pi over 2, we get 1, 0, negative 2 for my x, y, and z. So that's going to be from here, 1, negative 2 is going to be about here. So t equals 3 pi over 2 gives us the point 1, 0, negative 2. And then for 2 pi, we get x is 1, y is 1, z is 0, which is back to this point. So this is also when t equals 2 pi. If I then draw these dots together, connect the dots, our nice little complicated calculus version of connect the dots, then I'm going to pause this and make it nice. Okay, so I just redid that a couple times and got it all hashed out there. We note that when t is 0, we're here, we're moving in this direction, so it's nice to put these arrows to indicate our direction of travel. And that's it, that's my path. And we see that this is just going to repeat. As t keeps getting larger and larger, we're just going to keep hitting these same points over and over again at multiples of 2 pi, because cosine and sine have a period of 2 pi. We see this is actually an ellipse. I've got my z-scale a little bit shorter than my y-scale, so that's why this looks a little bit more circular than it actually is. But this is actually an ellipse with a z-axis, a z-axis, what's the word I'm looking for? Radius, there we go, is 2, and the y-axis radius is 1. And this is all just in the plane given by x equals 1. Let's go ahead and take a look at a GeoGebra version of this. We're going to be using GeoGebra a lot, and we're going to be talking about it a bit more on the next page, actually, and give you guys some instructions on how to use it. So you can go ahead and click on the link here, or you can type this in, copy and paste it, however you want to do it. Get this page up on your screen. Okay, got it. So here we see this graph. I have got this set up with this slider. I'm not going to explain how to do this in this problem because I've got an example where we're going to go through it in some detail on it in a couple of pages. You're welcome to pause and look through my code, click on the link, and hash it out on your own if you'd like, but I'm also going to do this in more detail, again, on the next page. So here I can see my slider is giving my t values, and we can see what points this corresponds to for different t values. Here is when t equals 0. If I swing this over, we can see in the y is z plane, this is the ellipse with a z radius of 2 and a y radius of 1. And as t increases, we move along the ellipse in this direction. Great. I said that we would also kind of see how this is constructed. If I get rid of this, look at these functions, it graphs them in x and y, which isn't my favorite, but here we're seeing my x value is just always 1, my y value is cosine of t is this gray line, and the z value h of t is 2 sine of t is this green line. We kind of put these together. The the x equals 1, I really want to just realize that that's giving us this x equals 1 should be here. I just want to retype it in. Oops. Why did it not like that? I see. My curve was defined via these f, g, and h functions, so it needed those to stay the same. But Here if I type in the plane x equals 1, you see that our vector valued function is, this space curve is staying in this plane right here. And our y and z values, so this one, it's hard to tell, if you took this and flipped it up, it would give us the up and down, the z values, and then this gray one's nice, it's corresponding to the left and right of this ellipse. Okay, let's get back to our worksheet here. Moving on to the next, this is an exercise for you. Go ahead and pause the video. Work through this on your own. Little hint, the period is different than 2 pi because of the pi inside of the sine and the cosine. Think about what the period is to help you think about what t values you're going to want to plug in for this. You can confirm your graph down here with this link. I will also go through this with you in just a few moments. Alright, let's run through this. I'm going to do this a little bit quick. Let you guys click on the link yourself. I have a class I need to teach in like 5 minutes. So exercise 1.2.2, sketch the curve given by the vector function r of t equals t times the unit vector I plus sine of pi t times the unit vector j minus 2 cosine of pi t times the unit vector k. So my x value is given by t, x equals t. My y values are given by sine of pi t, and my z values are given by negative 2 cosine of pi t. I see that the period of my sine and cosine functions here are going to be 2 pi over pi. So that's always, my period is going to be 2 pi over the b value given, say, sine of b times t. So this is my period. That told me I wanted to do t values from 0 to 2 to get one entire period figured out. And I did by 1/2, 0, 1/2, 1, 3/2, and 2. My x values are equal to these t values, so I get 0, 1/2, 1, 3/2, and 2. My y values, I plug these into the sine function, so I get sine of 0 is 0, sine of pi over 2 is, because when I plug in sine of pi times 1/2 is sine of pi over 2 is 1, sine of pi times 1 is sine of pi is 0, sine of pi times 3/2 is sine of 3 pi over 2, which is negative 1, sine of pi times 2 is sine of 2 pi, which is 0. My z values are given by negative 2 cosine of pi t. If I plug in 0 for t, I get negative 2 cosine of 0 is negative 2 times 1 is negative 2. If I plug in 1/2, I get cosine of pi times 1/2, which is 0. If I plug in 1 for t, I get cosine of pi times 1, which is negative 1. We multiply that by the negative 2 and get a positive 2. And then this is going to kind of repeat and get 0 out and then negative 2 out for when t is 3/2 and 2 again. So I plot these points. When t is 0, I get the point 0, 0, negative 2 right here on the z-axis. When I have t equals 1/2, I get x is 1/2. Move over here. Y is 1. Move out 1 in the y direction. Z is 0, so I can just plot that point right there. T equals 1/2 gives the point 1/2, 1, 0. When t is 1, we get the point 1, 0, 2. So that's 1 in the x direction, 2 in the y direction, none in the 0 direction. What did I say here? 1 in the x direction, 0 in the y direction, and then up 2 in the z direction gives us this point. And then when t equals 3/2, it's this point right here, which is, I'm pointing at it with my label. So t equals 3/2 gives the point 3/2, negative 1, and 0. That goes right here after I go 3/2 out this direction, negative 1 in the y direction from there gets to here, 0 in the z direction. And then we have when t equals 2, the point 2, 0, negative 2, so 2 in the x direction, 0 in the y direction, negative 2 in the z direction gives us this point. And we're going to get this spiraling ellipse again, except for the x values are now increasing. So my ellipse gets stretched out like a slinky, like a spring. So we get our elliptical motion in this direction like this, but gets stretched out in the x direction here. If you click on the link, you can see this in 3 dimensions and be able to like turn it around and take a look at it and see it in a bit more detail. All right, that is it for this exercise, and I will be I'm just going to pause the video, go teach a class, and come back and finish this video. So I'll talk to you guys shortly. Alright, and I am back. We now want to go ahead and show you guys how to use Geogebra a little bit. So go ahead, there's a lot of written out instructions here. I am not going to read all of this. I would rather go ahead and go through it with you guys a little bit more naturally. We have example 1.2.3, use software to view the following vector valued function in R3. R of t equals sine of 2t, comma e to the t, comma cosine of 2t. So go ahead and get a web browser opened up. Once you're here and have your web browser open up, go ahead and go to geogebra.com. And you'll go down to find the 3D graphing link right here under New Math Apps. Apparently I had something up here already. And I like close, the keyboard is here. I usually just type things out, so I close that out. And I want to go to my input. So I have a function. We know it's r of t equals sine of 2t, comma e to the t, comma cosine of 2t. And this actually is doing something here. We can see that we've got some bit of curve, and it does in fact give us something. I'm going to give a little bit more description and kind of get more of this curve to show up here. So I'm going to go and start over. And instead of typing r of t, I'm going to use the curve command. Curve. And we have a couple different options here. We see two expressions, then a parameter variable, then a start value and an end value. Or we could have three expressions, a parameter value, a start value, and an end value. So the expressions are our x, our y, and then in the second one our z value. So we want to use the second one so that we have three-dimensional coordinate x, y, and z. The parameter variable is going to be our t variable. Our start value and end values is what we're setting t to start at and end at, so that it knows where to start the graph, where to end the graph. So we'll choose this one. Oops. Choose that one, and I can go in here and choose these each individually. If we know what we're doing here, I can actually just type in curve. My x expression was sine of 2t. My y expression was e to the t. I use the caret symbol above the 6 to get into my exponent. I have to right arrow out of that. And then my z value was cosine. It's mad at me for something. Why is it mad at me? It thinks I'm done for some reason. I'm going to just close that. Just start over. I'm not sure why I was doing that. So if you guys run into computer problems, you'll see I do too sometimes, and sometimes you just have to scrap it. Start over. It's not mad at me now. So I've got my x, my y, and my z expressions in. My parameter is t. I'm going to start from, say, I don't know, negative 10 and go to 10. Okay, bring this back so we can actually see our graph now. And so we get this shape. So it looks like we have some sort of spring. And so here's my x-axis is the red axis, the z is the blue. So in x and z, we're getting circles. There we go, and that makes sense because our x and our z coordinates are given by sine and cosine, both of 2t. And we get a radius of 1 in both directions here. Now our y coordinate is given by e to the t, so as time goes on, our y value is stretching out more and more. As t goes to 0, our y value is 1, so we should get this point right here when t is 0. And as t goes to negative infinity, we see that my y value is getting closer and closer to 0, but never actually hits it. So I'm going to mess with the settings here a little bit. I can go settings, and we can change the color of our line. Move this out of the way so you can see it a little bit better. Oops. Settings of this. Make it blue. Go to my style and make it a little bit thinner. Now we see my line here like so. Zoom in. If I hold down the Shift key, it allows us to move the XY plane around. Like so. If we're here, if I go to the Z-axis, I can stretch my Z-axis. This allows me to undo. And we'll look if we get close in here. Come on, why is it not letting me zoom in more? It's mad at me. Oh, now it's real mad. Okay, hold on. I have no idea why I was doing that. It's being finicky today. It's normally a little bit better than this. Let's see. I want this. So going to my settings, actually thin this line out a little bit more. Super thin. If we were able to zoom in nicely here without this being all finicky on me, this coil, as y goes to 0, the t value keeps going to negative infinity, and it's just going to keep circling over and over again in the x and z direction while y gets closer and closer to 0. So this is an infinite coil. It keeps coiling up. There's an infinite number of spirals in here, in this tiny little y section. Now, a fun thing to do is I can now say, okay, so this is named a equals this curve. I can think of a as a function, say a of b, and I'm using b as a constant. Then I plug in and create a slider automatically for my b value. So b is 1, and we get this capital A equals little a of b. It's taking whatever this b value is here and plugging it into my curve up here for t. It recognizes t as the variable. It spits out this point, so I get this point on this line. And then I can use this slider and move the point along our line really quick. And this is something we're going to use in some detail. We're going to start looking at tangent lines off of curves to say what's the direction of my curve at any point in time, and we can get those tangent vectors to move with these sliders, create the tangent vector as something that varies with the input so that we don't have to do just a single static tangent vector but have it be more dynamic with these graphs. That's it. That's essentially all we need to do in order to create vector valued functions in our GeoGebra software. If you're trying to look to do this in a TI-89 or a Casio ClassPad, you can do it, but they render really slowly, and it is a giant headache, and it's really not something that's going to be necessary for a test or anything, so being able to do this in GeoGebra is going to be much more handy for you. Let's get out of this. So this is just written down a lot of instructions for this. You can click on this link, and it will pull up the graph that I just created for you. As your own exercise, 1.2.3, see if you can get this typed into GeoGebra, and then you can click this link to make sure that everything is working the way that you're expecting it to. I will click on the link in just a moment if you want to pause the video and give that a shot. If we go ahead and take a look at this graph here, I've got it pulled up, and I've kind of stretched it a little bit from the initial view. Also, this switched places with the above one. Sometimes GeoGebra will do that, not a big deal. But we get this crazy curve. From the YZ plane, we get this shape, and this is a little misleading on how many points it looks like we have 1, 2, 3, 4, 5 here. for t going through 2 pi times, this is going to happen actually where we get it 12 points in both the y direction as we're bouncing back and forth. If we look at this here, that's actually 2 separate points on the curve, not just one, and we've got to go through twice. So the least common multiple of 3 and 4 is going to be the number of points we get here in the y direction, and again in the x direction, same kind of thing. We'll see that we get all of these points here in the x direction. So we get this cool shape this way. We see that the x value is t squared, so we're going to get our waveform stretching out and getting wider the farther down in the t direction we go. So I can zoom out and see that that's actually happening there also. And yeah, hopefully you've got this all typed in and got that figured out. Let's go ahead and move on. I mean, the idea here is just to be able to, so that you can visualize things or graph things that you're having a hard time visualizing as we go through all these lessons. We'll learn how to use GeoGebra for planes and surfaces and all sorts of things as we go here. So this is just our first intro of getting you guys to use it. All right, our last topic of this lesson is intersections. So we are given a couple of different surfaces. Consider, let's just read this. Example 1.3.1, consider the two surfaces x squared plus y squared equals 4 and z equals x squared. Analytically determine the parametric equations for the curve of intersection of the two surfaces. So I'm going to walk through a number of steps here. I'm going to start by saying, what is the graph of x squared plus y squared equals 4 equal to? Or equal to, what is it? What is this graph? So if I note we are in R3, not R2 here. In this case, my z value is free because it's not related to x and y in any way. We can say let's get this drawn out here. We can say that x squared plus y squared equals 4 is going to give us circles of radius 2. Oops, that's not the prettiest. There we go. We get this circle of radius 2 when z is 0. So this is when z equals 0. But if z is 1, we'll get another circle. We'll just get the same looking thing, but up here. And if z is negative 1, we'll get the same thing, but down here. And if z is 1/2, we'll get the circle in between this. If z is 5, we'll get a circle up here. We can have different z values and get this entire cylinder. Great. So if we want to do the same kind of thing for z equals x squared, then I recognize, okay, I'm going to get a parabola. If y is 0, so here we have y is free because it's not part of this equation. So if y is 0, we get the parabola going through the origin, like so. So here's when y equals 0. If y is 1, we'll get the same kind of parabola but over here. This is not going to let me. Yeah. There we go. If y equals negative 1, we'll get the same parabola, but it will be starting over here. And we could do this for any y value, and we'll get these, or this parabolic cylinder now in this direction. Now, if I try and take this and draw the intersection, it's going to be a little bit weird. If I'm looking down on the xy plane, I'm going to do this in a couple of different views. But I take what we have here, if I'm trying to draw this looking down on the xy plane, let's see if I can. Does that work? There we go. Then well, the cylinder is going to look like a circle of radius 2. But the parabolic cylinder, if I'm looking down on the xy plane, it's going to look like it's taking up everything. Right? We're going to get these parabolas that look like these horizontal lines here. But since they keep going for any y value, it's going to look like it's taking up the whole plane. So the intersection from this view is actually just the circle. And this circle of intersection well, that's going to be given by x equals 2 cosine of t and y equals 2 sine of t. If I think about my unit circle, if I have x equals cosine of t, y equals sine of t, this is exactly our unit circle, right? So if we have a circle of radius 2, I simply stretch the x and y by 2, and that gives us a circle of radius 2. Go ahead and plot t values if you want to in here, and it should give you this exact circle. So that's great. What if I go ahead and look at this intersection, but look at it from the xz direction? Well, in this case, we see that the cylinder is going to be these vertical lines right here. And the parabolas will cut through here. Let's keep in mind that the cylinder also exists throughout this section, like so. So the intersection of these two, actually let's note that the parabolas keep going, but their intersection within this space is this part of the parabola where these are overlapping. Now, our goal, sorry, you guys couldn't see what I was writing down there. So x equals 2 cosine of t, y equals 2 sine of t. Take a second. Sorry about that. So our goal is to find a vector-valued function r of t equals. So this actually gives us our x-coordinate. It's 2 cosine of t. We're really done with that. And this gives us our y-coordinate, 2 sine of t. But we still need to see what our z-coordinate, z-component is. The reason that x and y is this is because we can see that from looking down just at the xy plane. We remember from the beginning that z equals x squared. And we have something for x. X is 2 cosine of t. So we just substitute that in to get 2 cosine of t quantity. All of this is being plugged in for x squared, so this is 4 cosine squared of t. And one thing that I really like to point out is anytime we're doing intersections of any two objects, so we could do intersections of lines, we could do intersections of surfaces, we could do the intersection of a line and a surface, or a space curve and a surface. We could attempt to intersect a point and a surface, and that's just asking the question, is the point on the surface? But no matter what, if we are looking for intersections of things, we will need to employ substitution in some manner or another. Now, depending on what kind of objects we are trying to intersect, that's going to change how we're doing our substitution. So if I'm trying to do the intersection of two lines in just x and y, then we could solve for x in one equation, plug it into the other equations, and solve for y, and then back substitute. In this case, trying to find the intersections of these two surfaces, it became necessary for us to get parametric equations for x and y for one of the views, and then plug that into and substitute that in for z from the other view to get our z component. So the substitution looks a little bit different, but in any intersections we are going to be using substitutions in some manner or another. So let's go ahead and look at this graph. Got to pull it up here. So we can see the red is the parabolic cylinder, the blue is the circular cylinder of radius 2, and the white is our curve of intersection, which I have plugged in here. 2 cosine of t, 2 sine of t, 4 cosine squared of t. So we almost get like this saddle shape. We see it's circular from the top view. We see it is parabolic from this view. We also recognize that it looks like it's a negative parabola from this view, which we didn't really explore, but we could go through and realize how y and z are related to each other as well if we wanted to go down that hole. Okay, but let's not do that. Let's go ahead and move on to the next page. So we got 2 more examples here, and then we are done for this lesson. Example 1.3.2, at what point or points does the curve r of t equals sine of t cosine of t, comma t intersect the sphere given by x squared plus y squared plus z squared equals 5? So if we want to intersect, this is a curve, and this actually graphs, we see in x and y, we have sine and cosine, so this is going to give us circles from the xy view, if we're looking down on the xy plane. But my z value equals t, so as t changes, my z value increases, so this is going to give us some sort of spring curve. We want to intersect this with this sphere, so we're asking, how is this going to intersect? That is horrible. A sphere, so it's going to intersect the sphere somehow in 2 points. So if we want to find these points, this is my x, this is my y, and this is my z for this vector valued function. So I can take these and plug them in for x, y, and z respectively in my sphere and see where we're going to end up crossing each other. So we get sine squared of t plus cosine squared of t plus t squared equals 5 when I plug these in for x, y, and z respectively here. I'm going to use the Pythagorean identity from trig that says sine squared plus cosine squared equals 1. And then I can solve for t here. T squared equals 4, so t equals plus or minus 2. So this is the t value in my vector valued function where the sphere and the spring intersect. But we want the points, right? At what points does this curve intersect with this sphere? So to find that, I'm going to take these and plug them back in and get r of negative 2 equals sine of negative 2, cosine of negative 2, comma negative 2, and r of positive 2 equals sine of 2, cosine of 2, comma 2. And while we could get approximations using a calculator, we are actually going to avoid that and just say that these are the exact points where this occurs. And we can go ahead and take a look at this graph here. And see that a much better version of my little sketch there. So we see the sphere and our spring, and we see the 2 points where that space curve intersects that sphere. Here are the decimal approximations if you wanted to look at those, where I've actually got the points as here's my curve, and I plugged in 2 and negative 2 into the t values to get these 2 points exactly. All right. Let's go ahead and move on. Last problem of the lesson. Example 1.3.3, given the two space curves r of t equals the vector 2t plus 1, comma negative t plus 2, comma t plus 3, and q of s equals the vector negative 3s plus 8, comma s minus 1, comma negative 2s plus 7. Determine if they intersect, and if so, determine if it is a collision. So here we're looking at two vector valued functions that are actually giving us the equations of lines. Both of these are straight lines. So if they intersect, they're going to intersect in a point, or they're not going to intersect. We'll talk about the collision in a minute after we work out the math. So if they intersect for two lines to intersect, the x, y, and z values. Oh, you know, I can zoom back in here. There we go. All need to be equal. So if we're thinking about how are we going to do a substitution in order to find if these intersect, well, that means that the x components, 2t plus 1, needs to equal negative 3s plus 8. The reason we're using two different variables for our inputs is that these times could be different, right? So s is a separate input variable than t, so that I'm not saying that this is just the x values could be the same but at different times. And so these could intersect, the lines could intersect, but the input variables could be different numbers for them to output the same point. So we don't want to have them have the same variable to assume that they're traveling at the same time. So for my second component, we have negative t plus 2 equals s minus 1. For my third component, we have t plus 3 equals negative 2s plus 7. So our goal now is to find if all three of these can be equal. I have three equations, two unknowns. For these to intersect, all three equations need to be true. So I'm going to start by solving for either variable in any of these equations. Here I see that it's super easy to solve for s right here. So I'm going to add 1 to both sides and get s equals negative t plus 3. I can now plug this into either of these two equations. I'm going to choose this one on the right. It doesn't matter. So this is t plus 3 equals negative 2 times negative t plus 3 plus 7. So t plus 3 equals 2t minus 6 plus 7 is plus 1. I want to solve for t now. Bring the 1 over, I get 2 equals. Bring this t over, and I get 2 equals t. So I could think about this a couple different ways. I'm just going to finish solving this out. But if t equals 2, and I plugged that in, I could say, what is r of 2? So if I take r of 2, I get 5 0, 5. So if t is 2, then what is s going to be? So I take this, I plug it back in over here, and I get s equals negative 2 plus 3 equals 1. And this, when s is 1, is going to give us so that the y coordinates and the z coordinates are equal, because we're using just the y and the z equations in order to go ahead and find s and t. If I try what is q of 1, because s is for my q function, then I get 5, 0, 5 again. So when s is 1 and t is 2, these cross the same point. So we can find it this way. We're going to confirm over here now. So if I take if s equals 1 and t equals 2, we get 2 times 2 plus 1. We're really asking, is this equation true? Does this equal negative 3 times 1 plus 8? Here we get 5 equals 5. Yes, so the x values line up when this s and this t value are used. So they do intersect. They intersect at the point. Five, 0, 5. No, it is not a collision, since s does not equal t. If these were the same, if I got when t is 2 and s is 2, that would mean that both of these lines are coming together at the point 5, 0, 5 at the same point in time, if we were doing this as where t and s were time variables. But since they don't equal each other, we're saying, okay, when time is 1 second, then our q function crosses through 5, 0, 5. A second later, when t equals 2, then my r function crosses through 5, 0, 5. So they're not colliding. They're going through the same point in space, but at different moments in time. We can go ahead and look at this graph, and we see the two lines here. Here's our point 5, 0, 5. This is programmed pretty weakly, just in that everything is static, or this point is static. I could have done both lines as curves and then done points that are moving with respect to s and t individually to see how they both go through the point but at different times. You know, I'm going to just do that. Give me a second. Okay. Went ahead and redid this. So we've got my q curve, my r curve. In fact, let's change the color so we can see them a little bit better. So q, let's make blue. Oh, r, we're making blue apparently. Q, we're making red. Let's make this point red to match. And this point blue to match the line that it's on. All right, so if I move my s and t, so here at 0, when s is 0 and t is 0, so at time 0, we see that on the r function, we are over here. On the q function, we're at this point a over here. As b goes to 1, so we go to 1 second. Then we see that on my q curve, it's now passing through the point of intersection, but my object on the r curve is not yet there. Still didn't want to give me exactly 1. When I go to time equals 2, now the object on curve q has passed through that point already. It's no longer there, and now the object on the r curve, point B, is there. And that is it. All right, so that is everything for this lesson. Thank you guys so much for listening. and I will talk to you in lesson number 2.